Our next speaker is Laurie Kirk, and she is a security researcher at Microsoft, Microsoft Defender. I've met Laurie before, but I don't know her well. So I had to ask around to find out what to say about her. And what I was told to say was that she's a badass, that she's smart as hell, that you should definitely watch her YouTube show, and that if you want to harden your application so that people like her can't reverse engineer it, then you definitely want to learn from her and follow her YouTube channel. So with that being said, Laurie Kirk.
Thank you. Hi, everyone. So, as you said, I'm Laurie Kirk, and I'm going to be talking to you about the art of runtime obfuscation in Android today. And by the end of this talk, you'll realize why that's kind of funny, hopefully. So, who am I? You've already heard. I'm Laurie Kirk. I'm a reverse engineer at Microsoft, representing myself today. And I specialize in cross-platform malware analysis and reverse engineering, especially focusing on mobile threats. And I also run a YouTube channel called Laurie Wired that dives into a bunch of different topics of mobile reverse engineering as well. So not too much on me, let's just dive right into it. What we're going to do during this talk today is we're going to make this, which is some really pretty nice Java code that if you're a programmer, you'll be very familiar with this, and you could probably just look at this and kind of figure out what it's doing if you took enough time. You don't really have to be a reverse engineer for that. And we're going to make it look more like this. So if I was looking at this for the first time, I would be like, what is this doing? I have no idea. And that brings me into kind of the primary reason for today's talk. We're going to be focusing on obfuscation and focusing on runtime manipulation in particular. But first, what is obfuscation for anybody who's not familiar? I promise that it's a word. If you put it in like Microsoft Word, it's not going to red squiggle, even though it sounds a little funny. But this is actually just a technique that is used to obscure the underlying functionality of all of your applications. And this is used among many different platforms. This isn't just specific to Android, it's for Windows, Linux, Mac. Particularly important for Android though, and particularly important for malware authors, and we'll get into why that is very shortly. But there are offensive and defensive reasons and motivations for obfuscation. This is particularly essential for Android since if you're taking a compiled Android application, this is called an APK file, stands for Android package. If you decompile this, whether it was written in Java or Kotlin by the developer, this is going to go back down to just pretty simple Java source code. And this even includes a bunch of the developer names and statements within the code, just throwing it into some open source decompiler like JDEX, for example. So talking about the different kinds and motivations for obfuscation, first would be defensive obfuscation. This is going to be the type of obfuscation that legitimate application developers will use to try and protect their source code. So they do this for a few different reasons. First thing is to try and prevent reverse engineers like myself, for example, from taking a look at their application code and actually stealing some of the source code. Next would be application size and optimizations for performance. I told you that an app has the original developer variable names inside of it. So one thing you can do, which is actually really common, is go through and remove all of those pretty developer variable names from that. That is overall reducing the size of the APK as well. Finally, the reasons could be tamper or vulnerability hardening. If you're trying to reverse engineer an application with the purpose and intent of trying to exploit it or tamper with it, if you can't figure out how it works, then good luck. There's no way you can actually write a custom exploit for it. And then the focus of today's talk is going to be offensive obfuscation. So this is going to be the tactics employed by malware authors, actually. So yes, they also want to prevent reverse engineering, but for very different reasons. Mostly they want to try and hide any of their malicious tactics that they're trying to employ. For example, if you have an application that was written that's going to steal all of your device's data and upload it to some C2 server, well, you don't really want somebody to just throw it in a decompiler and be able to figure that out really quickly. You want to be able to hide that malicious behavior. So that brings me into my last point, which is they want to mask the origin of the application as well. For example, if you have an application that is pretending to be a legitimate application, you can call that anything you want and get it put in the Android Play Store, Google Play Store, anything you want. And you can pretend to be that legitimate application. So they'll try and hide the fact that this is actually, in fact, a Trojanized app. This brings me into the techniques of obfuscation, now that we got a little bit in the background of what obfuscation is and what are the motivations for it. Really simple techniques are renaming identifiers, like I mentioned, inserting dead code sometimes, which tries to make reverse engineers be fooled into analyzing dead code, which is not actually called within the application, so that they'll miss the actual legitimate code within the app. So if you're distracted by other code, then maybe you'll miss something that's doing something really malicious. Next, we have string and class encryption. If I had, for example, a string inside of my app that said, in the process of stealing all of your data, I don't really want to have that just plain text on disk, so I would probably encrypt that value so that I couldn't just throw it in a decompiler and see that. Moving on to a little bit more interesting types of obfuscation. Really common technique is packing or reflection. So this is basically having additional code that is dynamically decrypted and loaded into the runtime state as additional executable files. So if you're looking at the right-hand side there, you see that app.apk. Remember, that was your Android application, so your Android package. That's kind of the top-level component of an Android application. So within that, you have your classes.dex file. So that's going to be important. So remember, dex stands for Dalvik executable. When I say dex, I just mean Android executable code. So that's going to be code that's going to be directly executed on the underlying device. So what a malicious application will really often do is they'll have another dex file that is stored inside an additional assets file and encrypted by the first initial classes.dex file. And then they will commonly use one of the standard class loaders, such as path class loader, dex class loader, in-memory dex class loader, to load that actual additional Dalvik executable file into the runtime state. And by doing this, they're successfully able to mask the presence of additional code, because if you took a look at that encrypted.json, it's encrypted, it doesn't mean anything to you, so you have to actually run the application to get that additional code. And by doing this, we have successfully manipulated the execution of the application to execute some additional code. Looking at the really primary reasons for obfuscation in Android, if you took a look at this, and maybe you have a little bit of programming experience, you could search and find a bunch of different kind of clues to figure out what this application is actually doing. First of all, you can see that we have the original variable names. You see that get main component name right there that's pointed to. That was the actual developer variable name, so that is not stripped when the application is compiled. Additionally, we have some logging statements here. Those are in plain text, as well as some plain text strings right there. You can see we're returning the value MetaMask. So looking at all of these, it's really easy to figure out what the application is doing. Which brings me to an obfuscated APK. This is a lot harder to figure out what it's doing. If you notice, we have stripped those pretty variable names, and the developer here just named it D. That's the method name. D stands for descriptive, of course. I'm just kidding. It doesn't mean anything. You can't actually tell what this is doing, but we also have some dynamic code loading going on. That call to dex class loader right there is actually taking the path to an additional dex file, or that executable file, on disk and loading that into the runtime state. Finally, we have this exception handler right here, and if you take a really close look, you'll see that it's returning a string concatenated together, and the variable is this.c.hd, which doesn't mean anything. This is actually an encrypted string on disk that is going to be dynamically decoded and then returned as the exception handler. So if you're trying to read this string, you have no idea what it's doing until you decode it. But one thing to note is that a lot of these techniques have been employed for a really, really long time. These are very easily recognizable. So for example, you saw I called out that dex class loader. That's part of the actual Android framework. So when you include that into your code, you actually have to import that particular class. So if I was opening up an APK in JDEX, and I do this all the time, one of the first things I do if I suspect hacking is I just hit the search text, then I type in class loader. It tells me exactly where that loaded class is, and then I can be like, oh, okay, I just need to hook this method to figure out the dynamically loaded code. So what can we do to actually bypass some of these commonly recognized techniques? That brings me into the primary topic of today's talk, which is going to be runtime obfuscation, which is actually manipulating the Android runtime environment. First of all, just to have a little bit of background into what the Android runtime actually is and how it works. The Android runtime, also known as ART, is basically just a framework that its purpose is to input those APK files, the Android applications, perform a bunch of different compilation, optimizations, and translations basically down to just machine code that is directly executable on the underlying hardware. And it's going to, in the process of doing that, store all of this Dalvik executable code that exists on disk, map that into memory, and then go ahead and parse those into runtime objects before it's actually going to be executed. So it's doing just a lot of different stuff on the back end. If you want to think about it simply, takes in application, translates it, and then executes it. So one fun fact is that this actually used to be the Dalvik virtual machine, but in previous versions, they actually switched over to ART. So this talk is going to be focused on ART since that is the latest available version. And this is designed specifically for Android devices to kind of account for the limited device performance and memory capabilities. Like, have your phone, it can do a lot less than your computer, so you need kind of a special runtime environment to actually account for that. So now that you've had a little bit of background, let's go into actually how to perform runtime obfuscation. So as I said, this is just manipulating that ART, that Android runtime environment, and this allows us to actually alter or even replace methods during the application execution time. So this would allow you to disguise calls to particular malicious methods. Additionally, you can have this perform different functionality while the application is running, as opposed to if I put this in my decompiler and saw this on disk, then I would not think that any of this is actually going to be executing. I would think it would follow the standard flow, but this causes Android to execute kind of an unexpected flow of control of code. So why would you use one of those standard class loaders like dex class loader, path class loader, in-memory dex class loader, when you can just directly modify the runtime? Or even why would you use polymorphism? Just kidding about that. So you should really definitely use regular polymorphism, or else you're going to have a very miserable time. So let's just dive into some background knowledge that you'll need in order to actually begin your manipulation of the Android runtime. So first of all, you need to understand some of the structure of the Android framework. So this is actually, we're going to end up diving into the source code of Android itself so that we can understand how to instrument this. So the Android framework, if you're an application developer, is going to be primarily written in Java. So your top level layer up here is going to be all exposed as Java methods, Java classes, and Java variables. So you import those, but what you might not realize is that actually inside of the Android source code on the back end, a lot of the functionality is actually implemented in native code. Native code in Android would be C, C++ assembly code that is compiled to run on a particular processor architecture. So you have your Java code that exposes to application developers, and you have your native code that is working on the back end. And the way that native code and managed code actually communicate with each other is through something called the JNI, or Java Native Interface. So if you remember, I said that the dex file was extremely important to remember during this talk. Dex for Dalvik executable. JNI is another one. This is our Java Native Interface. This is our bridge between native code and managed code. So we're going to be following this kind of three-step process while we're actually modifying the runtime. First is going to be hook, then modify, then execute. What we want to do when we're hooking is we want to remember that top-level framework. That's going to be our Java framework. So we want to pick a target Java method, variable, or class that we think is interesting based on reading the Android source code, and we think contains important data that we would actually like to manipulate and modify. So once we've picked our target after like 20 hours of going through the Android source code, which luckily you won't have to do today, we will use the JNI, that bridge between native and managed code, in order to actually hook, get a handle, or a reference to that particular Java method while it's running. Next, once we've actually hooked our target method of choice, we want to typecast that, because we're going to be working in native code actually to perform this ourselves. And we want to make sure we typecast that to the correct pointer type. You can do void star pointer, or if the variable you're looking at is some kind of different data, we need to just analyze the source code, figure out what it is, and account for that accordingly. But then once we've done that, we can modify the underlying C++ structures that are actually the underlying implementation of that code. Finally, execute, pretty self-explanatory. We've done our hook, we've done our modification, now we're just going to execute the unexpected code. So 2 techniques to perform this kind of runtime manipulation would be intercepting class loading, and in that one, our target in the Android framework is going to be the dex file class. And the second technique would be hooking and manipulating runtime objects. So our target for that is going to be something called the ART method object. First of all, let's get ready. This is going to be diving really deep into this. So this is the first technique, is going to be intercepting class loading. So background into the class loading process so you can understand exactly which portion we're intercepting. This is the kind of very high-level application lifecycle for an Android app once the user starts and decides to run it. You have your APK, which is your Android package. That's your application that's on disk. That contains your executable code, the dex file. The user hits that button on their home screen and actually launches the application. And then that triggers something called the loader to actually take all of that data that's related to that APK, in particular the dex file, and map that into memory. So you can't directly execute a file from disk. You have to actually map it into memory before you're able to execute that on the underlying processor. So once it's been loaded and mapped into memory, the runtime, that ART, Android Runtime, starts parsing that memory mapped data right there, and it puts that in supportive runtime objects and structures that are designed to point to the data on disk, as well as point to different data in the runtime environment, so that it can actually execute that code, which is the last step here, where the runtime actually does the execution on those parsed runtime objects. And this is the Dalvik executable format. This is what it looks like on disk. So this is kind of interesting to keep in mind, because it also, the runtime environment uses a very similar methodology. You'll recognize a lot of these variable names, since they're used inside of the Android source code as well. But you have your dex file structure in the middle right there, and everything is ordered by different data structures and types. If you take a closer look, for example, at that class defs section right there, you have to kind of follow this really long, complicated pointer trail to actually get to your underlying method and your underlying instructions that are part of your method. So you have your class def item, then you have to go to that class data offset, and then you have to follow that to your class data item all the way down until you get to a single encoded method. And that is just one method that is part of your application. And if you continue following that along, you'll actually get to your array of instructions that's directly executable. So you have your dex file on disk. It's going to be inside of your APK file or your application. And each dex file that's defined on disk actually receives its own instance when the application is running. So this dex file instance right there is defined in Java. So every dex file on disk, or any dex file loaded using those dex class loader, path class loader, etc., are going to receive their own dex file instance when the application is running. So what we want to do if we're trying to hook here for our hook, modify, execute methodology, we want to hook that runtime object. So let's get into actually how we would go about doing this. So this is the first example where we're intercepting the class loading process. So we need to actually let our dex files that are going to be our targets get loaded into the runtime, whether that's the dex file on disk or using our standard class loaders to load the files. Then we want to select our particular object of interest that has data we want to manipulate. So here, after looking at the Android source code for a very long time, we've determined that this highlighted mcookie object right here actually contains really relevant DEX file data that will allow us to manipulate the runtime. So once we've determined that our mcookie field is our target, we want to actually use that important Java native interface that I mentioned before to actually get a hook or a handle to that particular mcookie field. And I'll show you the code for how to do this in a little bit. One really interesting note is that if you see here, private object mcookie, that's a private object. You shouldn't be able to access that. But the Java native interface actually by design bypasses standard access modifiers. So finally, when we get to this point, we're able to actually swap the pointers associated with this particular mcookie object that's pointing to some DEX file data. This is just taking kind of a closer look, and this is referencing the Android source code right here. So we have our mcookie, which is our variable and our object that we're going to be modifying. These are some other variables that are associated with the DEX file class defined in Java. So each one of these DEX files is given their own Java instance. And this is actually just an in-memory representation of a DEX file. And they actually put that in their comments inside of the Android code. So that's really helpful. Like, thank you Android developers for being very descriptive there. So we can actually swap these two fields and swap the associated DEX files. And this is the code to do just that. So if you're trying to understand what's happening here, if you look at that env right there, env and then the arrow and then the find class, this is referencing that Java native interface bridge between native code and managed code. But not only is it used inside of the actual Android source code, we can use the JNI in our own application code in our own Android applications. So we're getting a hook to that DEX file Java class that was defined inside of the Android source code. Then we're getting the associated mcookie field. If you look a little below that, we're still using the Java native interface to get hooks to these particular fields. So we need two instances of these. The first is going to be the instance of the one that we want to replace, and the second is going to be the instance of the one we want to replace with. So once we have those, we can actually go ahead and take a look at the data that mcookie is pointing to and swap all of those associated pointers inside of the mcookie. So you might be wondering, what exactly is the mcookie field and what is that pointing to? Let's take a closer look. So this you can see for yourself if you look at the Android source code, but these are actually long pointers to different objects inside of the Android runtime. So the first one is oat file. You might be thinking, what on earth is that? You've mentioned DEX file, but what is an oat file? And why do I care? Oat stands for ahead of time with kind of a different twist. I don't know. They put them backwards, but oat file it is. And this is just an optimization by the Android runtime to try and ahead of time compile part of your application code for performance reasons so that it's not compiling and executing on the fly every single time you're trying to run an application. Below that, you actually have another long field, which is a pointer to your DEX file object. Remember, that's defined in the Java code, and that contains all the data related to the DEX file. So there are going to be as many long pointers here for as many DEX files that you have inside of the application. So that could be n number of DEX file pointers right there. So you need to be able to know how many DEX files you have and modify each one of these. So then you'll need to manipulate the data inside of the DEX file object and as well manipulate the data inside of the oat field. So if you try to just manipulate one of these, like if you're trying to manipulate the oat file pointer or just trying to manipulate the DEX file, remember that's your executable code pointer, you're going to probably either break the application or maybe cause some really unexpected code to execute, or maybe you're going to do nothing at all because it was already compiled and it didn't even see that you tried to manipulate the runtime. So make sure you're manipulating all of your pointers and you're not just simply manipulating the first one. This is taking an even closer look at another option of what we can do once we've actually hooked this target method. So this is our dex file, but this is the native C++ version of that dex file object. So this has all of the associated pointers and data that is connected to this particular dex file. So what we want to do here is we want to use some cool pointer math to actually calculate the offset to the field that we want to modify. In this case, we're looking at the class def field that we want to actually modify and change the data within. And then going back to that Dolvik executable file structure that I mentioned previously that is important, you can follow that class def definition there down, remember that pointer trail to get to all the instructions, and actually modify or swap two different classes within this dex file. So each one of these class data offsets points to a separate class that's defined in Java or Kotlin somewhere inside of your Android application. So that's how we could actually modify the class loading process and modify the different objects that are associated with that. So that was a lot of information to throw at everybody, so I hope you're still awake. And if you're not, this next process is kind of similar, so here's another chance to try and understand and follow along. And if you're like, oh, that was really easy, well, this is another technique that's just kind of similar. So here we go. The second method that we can use is actually modifying runtime objects after they've been taken out of the dex file, mapped into memory, and then parsed into all of these different associated runtime objects. One really important object that you need to consider is the ART method. So remember, ART, Android Runtime. So that's your runtime environment. So ART method kind of makes sense. It's just a method inside of the runtime. So each method that's defined inside of your dex file, inside of your application, is actually going to get its own ART method instance while it's running. So this is defined in a Java class, so if you're familiar with object-oriented programming, you have your method defined on disk, then you get an instance of that Java class for every single method inside of that original dex file. So the data inside of this ART method object is related to a single method, but it references some of the method data that's defined on disk, as well as some of the method data that's defined within the runtime. So it's just got pointers going to many different locations, and it's really confusing to read, but we'll do our best to look at some of the high-level source code to try and understand and figure out a target within this, try and hook and modify. So again, this is the same kind of concept as the dex file. You have your dex file on disk, it gets a dex file instance when it's running. Here you have your Java class that has methods inside of it. You have your normal method definition right here. You also have an additional malicious method definition. Each one of these is going to get instances of the ART method object during runtime. And you want to actually hook the runtime instance, because if you try and do something to the dex file on disk, remember, we can't directly execute the dex file. We have to directly execute the parsed compiled code on the underlying system. So that hook is going to go somewhere right in between there once we get to the actual runtime state. So let's look into exactly how we would perform this. We're going to be trying to swap the entry point code. So the entry point code is going to be the actual compiled machine code that's about to be executed. So if we hook the entry points of two particular ART method objects, we can actually swap code that gets executed if you call one method to the code that's going to be associated with another method. So remember, we're following our hook, modify, execute kind of methodology. So this is the hook stage. After another 20 hours of diving into the Android source code, we actually found this ART method private long field that's inside of the Java lang reflect executable.java. If you're looking on the right-hand side, this is actually part of the Android source code that we have spent time to look at and figure out the fields of interest that are related to our ART method objects. So now we're hooking that ART method object. And remember, we're trying to calculate the offset to the entry point code that's about to get executed, and we want to be able to swap those pointers. So we're going to have to do a little bit of math and account. If you see, there's a bunch of variables above that ART method field right there. We have to calculate the size of each one of those and make sure that we're using pointer math towards the entry point and not accidentally modifying another variable. So then, once we've actually done our calculations, we are able to do the modify portion of our hook, modify, execute methodology, and we're able to swap the pointers to those two entry points. And consequently, we hit our execute stage, which is going to be executing different code. And this is kind of a high-level view of doing just that. You see, we had to account for every single variable that came before that entry point from quick compiled code, and that is going to be the place that we're going to be modifying. Just a couple other interesting fields in here. This is related again to that Dalvik executable structure that we saw on disk. If you see, what's really nice is the Android developers follow that kind of naming conventions as well, which thank you so much again for doing that, Android developers. But we're able to see that we have our dex method index, which we could find the code for online. And we have calculated those offsets, and now we're going to actually swap the entry points. And this is an example of doing just that. We have our normal method, and we have our malicious method. So we used that Java native interface inside of our native code, inside of our application that we're writing to actually perform this runtime manipulation. We went ahead, hooked those, and then we did our math to calculate the offset to each of the entry points of our target methods that we're trying to mess with. And then we can actually swap those two entry points. So once we've done that, we have a call inside of the class to myJavaClass.normal method. And what do you think is going to get executed? It's not going to be the code or the entry point that's associated with my normal method. It's going to be the code that's associated with malicious method. So consequently, we have performed the execute portion of our methodology, and now we have our bad code that's actually going to get executed on the system. So that was another example. Hopefully that one kind of clarified the process and showed how we could actually intercept the class loading process as well as modify methods after they've already been parsed and loaded into the runtime and put inside of their respective objects. Now let's look at some real-world challenges and use cases, because you might be thinking, well, if it's that easy, why doesn't everybody do it? Well, the answer is it's really not easy. It's actually very complicated to do this in your code itself. So let's talk about some of the challenges. One of the primary challenges is that it's just really complex when you have your code. So the main use case for this is actually custom packers or obfuscators. Remember, your packers were the things that had additional Dalvik executable files that loaded extra code. And then you have a lot of open source or publicly available obfuscators that you can buy. And those will go through and they'll try and mess with your code so that if anybody is taking a look and decompiling your APK, they can't figure out what's happening underneath. So this is just another one of the tools that is available to people who want to buy or use the open source versions of these. So they are commonly implemented as native libraries. So if you're not aware, Android is actually just Linux under the hood. So they're imported as native shared object.so binaries inside of the code. So now you have your custom obfuscator, which is doing all of that complicated pointer math under the hood. And then if I'm a script kiddie, I just import that into my application, and I have to call like library.hook and replace, and it's just really simple for them. And this is an actual malware sample that is using runtime obfuscation to try and mess up its flow of control. So if you're able to see that there, they are actually calling one of those custom obfuscators, and I'll link to that in the end of this presentation if anybody's curious. So all they need to do is they need to have the class names and methods of the targets that they're wanting to hook and replace. So then at the very bottom there, we have this hookmain.e call, and this is going to be doing the actual method swapping. So that looks really simple. All they need to do is just call that, and then it's performing that runtime manipulation and obfuscating what is actually executing. So this is a further part of this same example, and this is going to be replacing the onResume method of a Trojanized version of WhatsApp. So they could have all of the legitimate code of the WhatsApp application, but then they sneak in this tiny bit of additional code that's actually going to be performing the runtime manipulation. So then they call this on resume, so this is going to be replacing actual on resume method that is usually associated with WhatsApp. And of course they put in on resume haha because they're switchy and they can. So even though they're using this complicated obfuscation, they have like nice plain text strings for us, so yeah, kind of funny. But they are actually using this runtime manipulation. So going back to the challenges associated with runtime manipulation, what if I told you that you make one teeny tiny mistake inside of your calculation code, calculate the offset to a variable incorrectly, or you're off by just a single byte? This could break the functionality of the entire application and even cause the app to crash or just behave unexpectedly, or maybe just like not execute your code at all. So you want to be very, very careful how you're calculating all of the offsets to. So as I said before, the main challenges are complex implementation. And another additional challenge is that, so Android releases a bunch of different API versions. These are just different versions of Android that are released. You have like your API 28, 29, maybe. When you're using this runtime manipulation, there are small differences in the actual Android source code between almost every single API version for the methods you're looking at. So you have to account if they added an additional variable, if they change the size of a variable. You need to account for that in your code. So basically, when you're performing this, you have one very large if statement or switch statement that's checking if API version is this, then you need to calculate it this way. If API version is this, then you need to calculate it this way, and so on. So this leads into the third challenge here, which is some kind of brittle code. If you did not keep up to date, and somebody's running an API version that you don't have support for, then you're going to calculate this incorrectly, most likely, and the application isn't going to perform as expected. Final challenge would be timing issues. So for the code loading process and the runtime process, it might be a little bit difficult to actually time when that code is getting loaded, so you might need to actually re-trigger code loading or re-trigger compilation of the method that you swapped. If you remember that weird oak file, that ahead of time compiled file, you might have to have that regenerated when you're performing this manipulation. But if you're able to successfully do this, some of the resulting obfuscation benefits are pretty cool. So you're able to execute some unexpected code. And if you remember that dead code, that technique of obfuscation, this actually makes it look like the methods that you're replacing are dead, because if you open up your decompiler and you hit the cross-references button, it will usually say any method calls that actually call your method, but that'll just show you a blank list. You're not going to see any calls to this. So it might cause a developer to, or a reverse engineer to completely ignore this code and not realize that it's performing any malicious techniques underneath. Also, if you're using the ART manipulation, this bypasses that standard class loader call. So you remember the dex class loader, which all I had to do was press search text and then search for class loader. This entirely bypasses this. So you don't have those super obvious imports, but you're kind of doing the same thing by manipulating the runtime environment, just in a little bit more tricky way. The last benefit is you'll thoroughly confuse your reverse engineer, like myself, for example, and that's kind of interesting, to make different obfuscation techniques to make somebody's day just a little bit better. Keeps them on their toes, it's covered. So in conclusion, let's just cover all that we covered today. It was actually quite a bit, but it didn't seem too long, I hope. So we looked at the different obfuscation motivations and techniques within Android, and we looked at how we could use these obfuscation techniques to protect the underlying source code of our applications so that we could prevent reverse engineering for legitimate or malicious reasons. We also looked at the runtime obfuscation techniques to subvert the class loading process, where it's mapping the dex file or the executable file on disk to the memory objects. And we took a look at the second technique, which was to let the class loading process finish and parse into our runtime objects, and how we could mess with those objects after hooking them and changing some of the pointers within them. And finally, we talked about how this is generally packaged as custom packers or obfuscators just due to the challenge of writing this. The next steps, if anybody was interested and enjoyed some of this, you can actually look at this yourself. You can find the Android source code online available for you. It's actually got a really nice GUI interface that you can just step through, kind of like an online IDE. And you can look at trying to modify the instructions array associated with a particular method directly. And I'll actually be really happy if you do this because I haven't finished this one yet, so let me know if anybody is able to. So thanks so much, everybody. I really hope that you took away something, at least learned what a DEX file was, if nothing else, or maybe learned how to subvert the Android runtime. So any questions? Oh yeah, like there's a ton of different packers like DexCard, RogueGuard, a million of them, so they're commonly recognized by different ABs and stuff, or if there's a custom malicious packer, if you're writing a detection, try and detect that, it's actually kind of nice, because if there's encryption code that's really unique, you can easily detect that and find all instances using that packer. Not to my knowledge. It pretty much hopes that flow of control will follow as expected, because it's like, are you crazy enough to actually modify the runtime? Because it will pretty much just break if you don't. So maybe they should add some checks for that. Yeah, they're kind of assuming that as an application developer, you don't want to break your own application, hopefully. All right, well, if anybody's interested, there's some bonus stuff at the end. I'll make these slides available. It just shows all of the different associated source code inside of the Android framework if you wanted to study and start it yourself. Yeah, all of the DEX file in your method. And that's it. So thanks again. Thanks so much, everyone.